when you think of a robot, you think of something you see here in the slide. So you have a motor in there. It's a rotating motor. It has a gearbox to it. And we can build quite some interesting creatures with this. And we've been working on these kind of motors for the last 200 years, easily. The problem is these motors are usually loud, and they're kind of unnatural in the ways of how you interact with them. You not necessarily want to have a bigger size of this robot walking around in your living room. If there's a malfunction, that might not be great. And the noise is another big issue if you have motors that are loud and noisy. So the problem here is, if you look at nature, you don't have rotating motors, but nature uses wiggling, undulation, and other sort of motions to, for example, swim underwater or even to move on Earth. So if we take inspiration from nature, and nature can self-heal, it can use all of its built-in mechanisms, what biology has developed over all of evolution, why don't we learn these processes and apply them to how we build robots? So one thought is, if you think of a ship or of a boat, you think of something that has a large spinning propeller on the back. But what if you would build these kind of vessels using an undulating tail, or like just the back of this ship would wiggle like a fish, for example? So if we apply the usage of soft materials and also of muscles for building machines, we might be able to come up with a whole kind of new generation of machines. So here's an example where we took inspiration from nature, and it's a bit non-fluent, but I promise you it actually swims fluently. It just doesn't look to you like this. And if you're curious to see it, I will have some videos later on downstairs. So this is a fish that uses a tail that undulates back and forth, and we're flushing water back and forth in its tail, and it causes it to swim like a fish does. And with this, we were able to do biomimicry in a coral reef. So we could use this kind of creature with a camera on board and with some other sensors to actually observe marine life. And we're trying to understand, can we use a more biomimetic motion to maybe get other behaviors out of these observations instead of having fast spring propellers there. But there was still a problem. This fish here, it's called Sophie, is using a motor for its pump, because the pump that is flushing the water back and forth inside of the tail still uses this electromagnetic principle. So what we now have been doing is, let's just go back to the inspiration of nature. Let's build muscles that actually act like muscles. And here we're building our first prototypes of building a leg that can jump. So here we're not using any more rotating motors, but instead we're using silent electrostatic muscles. And so I can show you some of them later on. They're actually right behind me. I have one of these muscles there. And the way they work is you basically have a set of sheets, and you have oil that you put into these. And then you apply an electrode layer on top of it. And with this electrode layer, you can use it like a capacitor. But if you remember capacitors from your physics education, they were usually very rigid and like metal pieces that cannot move. But here, the parts that are surrounding this can move and can deform. And with this principle, you can achieve contractions. And I'm happy to show more details about this when you come by later. So with this principle in mind, we can also build fish, for example. So instead of using a pump, we put this muscle into the structure, and then this thing can swim. And similarly, the question now is, if you design these systems, you don't really know where to begin, because the muscles are not quite the muscles that we find in nature, at least not yet. So what we then do is we're using a way of generating a large design space where we start off with an initial design, and we're using design optimization techniques that can come up with new creatures that we have not seen before, that might be able to swim faster than an initial design an engineer was coming up with. So here you see how we kind of interpolating, for example, between 3 different fish shapes that we define, but you can do this with as many designs that you can come up with and continuously interpolate between those to come up with a better and faster swimming fish robot, for example. But now, to take it a step further, because I was saying nature is doing a really nice job in being self-healing and being efficient, why don't we build them with actual cells? Why don't we build muscles from cells? Tissue engineering has started to do this for applications where we put them into our body. Why don't we also use this to build our robots with these same principles? So we could be growing cells, muscle cells, and actually build a muscle that we then stimulate and cause it to contract. So, oh, by the way, what you're seeing here, this is a microscope image of these muscle cells that we've grown in our lab. And you see both the myotubes and the cell cores in here, for example, in different colors. So this is how it looks like when you start working with this in this area. And there's a couple of researchers that are very in the forefront of having started to do tissue engineering for robotics, but you're basically growing little muscles. You could think of this as a food source of making artificial protein, but we can also think of this as a way of building muscle for our robots. And so what this ends up being is you can make, for example, here's 2 little hands or 2 little fingers. They have 4 muscles that you see up on top. And when you electrically stimulate them, you see they contract. And all they're doing is they're basically converting chemical energy into muscle contractions, just like your body does. So with this in mind, I would like to close, and I hope I'm good in time. All I want to try to tell you is we need to rethink how we build machines. So I'm a roboticist, I work on robots, but this really applies to any kind of machine that we use these days. Do we always have to use electromagnetic motors or even combustion engines to achieve locomotion or other motions that we want to have? No, I don't think so. I think we need to rethink how we design machines, and maybe in the future, we can have a future with machines that are more sustainable, that might biodegrade by themselves, and they're going to be silent, not causing us to have tinnitus, and they're actually going to be sort of cute to have around and actually something I want to have in the living room. Thank you.